In Part 1, we discussed the history of certain designs that were conceived to use mixed propulsion from the start. In this episode, we will go over designs that originally made use of a single form of propulsion, but were later modified to take advantage of mixed propulsion. We will also go over the more limited range of composite aircraft using turboprop technology. Welcome to the Index of Oddities, where we discuss the lesser-known and more unconventional designs that often go forgotten in the skies of aviation history. Many of you are familiar with the Douglas BTD destroyer, a dive bomber that only saw limited production due to the project's termination with the end of the Second World War. While the BTD itself was never produced as a mixed propulsion aircraft, there were two prototypes, designated XB-Pt.2, that installed a Westinghouse 19B turbojet in the aft fuselage, providing an additional 1,500 pounds of thrust. This would be Douglas's first aircraft equipped with a jet engine. The design required the fuel tanks to be moved into the internal bomb bay to make place in the tail for the jet engine. An air intake would be placed right behind the cockpit, leading to an inclined turbojet, with the exhaust exiting the belly of the aircraft. This inclination was an interesting choice, as it was directing thrust slightly downwards, diminishing its effectiveness. It also resulted in directing hot exhaust directly onto the wooden decks of the aircraft carriers it was designed to operate from. Of the two prototypes built, only the first would be flown, taking flight in May 1944 before the project was dropped. The non-optimal engine placement meant the aircraft lost internal payload capacity, with only a marginal and unsatisfactory increase in performance. This resulted in the XB-Pt2 being abandoned shortly before the end of the war. The Douglas A-26 Invader is a well-known light bomber and ground attack aircraft used extensively throughout the Second World War. It was equipped with Pratt & Whitney R2800 radial engines. The only relevant variant for us is the Douglas XA-26F-DL, which included the addition of a General Electric J31 in the tail section of the aircraft. To supply airflow to the engine, an intake would be fitted in a dorsal position, where a defensive turret would normally be fitted. In addition to the turbojet, the XA-26F differed from conventional A-26 by adopting four-bladed propellers and large spinners to improve aerodynamics. With all three engines in use, the XA-26F could achieve a top speed of 435 miles per hour, offering only a marginal increase in performance compared to the also in development XA-26D-DL, which lacked the turbojet. Neither the XA-26F nor XA-26D would see production, as the contracts were terminated with the end of the Second World War. In 1945, a surplus B-24M arrived at the NACA Lewis Laboratory, now Glenn Research Center, where it would become one of the laboratory's most used aircraft. The airframe would be used extensively to study different icing phenomena on components such as windshields, propellers, and antennas. NACA would use the B-24 for nearly a decade to study these effects, perhaps the most interesting of which included jet engine testing. Modifications to this B-24 would include the removal of all defensive gunners. The leading edges of the wings and the tail surfaces had a thermal de-icing system installed. The aforementioned installation of a jet engine would fit a General Electric I-16, later known as the J31, into the aft fuselage. Airflow would be fed through an induction air inlet installed in a dorsal position. Windows were even installed inside the aircraft on the air duct in order to visually observe the ice formation during testing. Flight testing would occur at varying altitude, allowing for an inlet air temperature of 15, 20, and 25 degrees Fahrenheit, with a constant airspeed of 180 miles per hour. A water spray system was installed in front of the air intake in order to artificially simulate icing conditions, when only light natural icing conditions were encountered. However, this system had limitations, as it could only increase the icing effect in natural icing conditions, being unable to work in drier air. It also lacked the capacity to simulate the desired severe icing conditions entirely. The testing would result in a loss of thrust, ranging from 5.5 to 13.5%, and fuel consumption being increased anywhere from 6.5 to 17%. The obstruction to airflow caused by the ice varied from 32 to 75%. The B-24 would operate in this configuration for 54 hours of flight time, about 20% of which the I-16 engine would have been partially obstructed by the ice. There was no noticeable permanent effect on the engine, and it still operated as expected. Later tests would also be conducted with a Westinghouse 24C mounted underneath the right wing. However, information regarding that modification seems more scarce. The Convair B-36 Peacemaker was arguably obsolete by the time it was introduced in 1948. By this time, piston-driven fighters were beginning to be phased out in favor of first-generation jet fighters. However, it seemed jet technology was progressing a bit slower for large-scale jet bombers, and its jet-powered competitor, the Boeing B-47 Stratojet, would not be fully operational until 1953. Early Peacemaker models were equipped with 6 Pratt & Whitney R-4360s mounted in a pusher configuration. With the introduction of the B-36D, Convair added a pair of General Electric J-47-19 turbojets under each wing, where it earned the slogan, 6 turning, 4 burning. The addition of the jet engines greatly improved takeoff performance and dash speed. In order to conserve fuel, the jets would be shut down during normal cruise. Normal cruise varied based on model, with the fastest version having a cruise speed of 230 miles per hour on piston power alone. When operating all 10 engines, the B-36 could exceed 400 miles per hour at the cost of reduced range and excess fuel consumption. In 1951, the USAF requested an all-jet version of the B-36. As a result, Convair took a B-36F and modified it with a swept wing, and added 8 Pratt & Whitney XJ-57 turbojets in place of the piston engines. The new aircraft was designated YB-60, but never made it into production as it was deemed inferior to Boeing's B-52. The Fairchild C-119 flying boxcar saw a few modifications, upgrading it to a mixed propulsion design. The first was the AC-119K Stinger, a gunship variant that included 2 underwing General Electric J-85 GE-17 turbojets. This variant was armed with 4 7.62mm miniguns and 2 M61 Vulcan 20mm rotary cannons. There was even a mixed propulsion civilian conversion for the C-119, known as the Stewart Davis Jetpack. This modification mounted a single Westinghouse J-34 in a nacelle mounted in a dorsal position above the fuselage. The last model, known as the Stewart Davis Stolmaster, was a one-off conversion done in 1967 that attached 2 Westinghouse J-34s under the wings, similar in configuration to the aforementioned AC-119K. Another product by Fairchild, the C-123 provider, is another military transport with an interesting history. In brief, the design started as an experimental unpowered assault glider designated XCG-20 before being developed into the C-123 as we know it. By 1962, the C-123K variant was evaluated with 2 auxiliary General Electric J-85 turbojets once again mounted under the wings. The USAF quickly began upgrading 180 C-123B models to the C-123K standard. This would be the most produced mixed-power modification of the provider family. The C-123J was equipped with wingtip-mounted Fairchild J-44R3s. A total of 10 C-123Bs would be converted to this configuration on the production line, with 1 more later being converted for the FAA. The experimental YC-123H would also use the same J-85 engines as the C-123K, but would also be equipped with a tracked undercarriage instead of a conventional wheeled configuration. Only 2 prototypes of this configuration would be built. The C-123 would also see a pure jet-powered version tested, designated XC-123A, that was equipped with 4 General Electric J-47 turbojets. The Lockheed P2V Neptune began as a private venture, with design work beginning in December 1941. It was a land-based maritime patrol and ASW aircraft designed to replace the older PV-1 and PV-2 aircraft. Initially equipped with 2 Wright R-3350 engines, the P2V-5F and P2V-6F modifications would include the addition of 2 Westinghouse J-34 turbojets mounted in pods under the wings. All 4 engines were configured to burn the same 115 to 145 octane avgas. The jet pods were equipped with intake doors that would remain closed when the engines were not running, to reduce drag and to prevent windmilling of the fan blades. When flying low-altitude missions, the jets would be kept running at idle as a safety measure, should the aircraft encounter an engine failure in one of the piston engines. The Canadian-operated P2V-7s, designated CP-122, would also later be fitted with the external jet pods. The Neptune was only ever modified to take advantage of jet propulsion after the successful results of the Martin P4M, which we covered in Part 1. In 1943, the U.S. Army Air Corps sought out a new escort fighter to provide cover for the soon-to-be-introduced Boeing B-29 Superfortress. The requirements would demand an operational radius of 1,250 miles with fuel for 20 minutes of combat and a reserve supply for landing. It would require a cruising speed of 250 miles per hour, a maximum speed in excess of 500 miles per hour, and a combat ceiling of 37,500 feet. Consolidated Vultee submitted an aircraft to meet these requirements, designated XP-81. To avoid any confusion, you may often hear the XP-81 being a consolidated Vultee, or Convair product. The XP-81 started development under Consolidated Vultee, however the company was later renamed Convair while the XP-81 was still under development. All of these names are technically correct. During the early stages of development, Consolidated Vultee considered the use of the proven Pratt & Whitney R2800 radial engine, but eventually settled on the General Electric T31 turboprop, a new unproven yet promising turboprop engine. In the rear of the aircraft, situated immediately behind the cockpit, was a General Electric J33 turbojet. As was common with these new engines, the T31 ran into delays, and by the time the first XP-81 was ready, the T-31 had yet to be delivered. The Air Corps quickly provided a supplemental Packard-built V1650 Rolls-Royce Merlin, taken from a P-51D. This temporary engine increased overall weight by 950 pounds and reduced overall power by 1,720 horsepower. The XP-81 first flew in this configuration in February 1945 and would continue to fly with the Merlin through May of the same year. Over this period, the XP-81 would conduct 46 test flights, accumulating just shy of 48 flight hours. By June, the T-31 engine would be installed, where the XP-81 would conduct ground tests through December. The ground testing revealed a number of issues related to the T-31, including problems with the propeller control and difficulty starting the engine. There was also unacceptable throttle lag, with test pilot Frank Davis noting about 10 seconds of lag when applying power, which could prove to be detrimental in the case of an aborted landing. After a small number of changes, the XP-81 once again took to the skies on the 21st of December, 1945, this time equipped with the T-31. 69 test flights would be conducted in this configuration, however only 42 hours of flight time was logged, with the T-31 being a constant source of trouble. As such, Consolidated Vultee proposed a variant equipped with a General Electric TG-110. However, the Army Air Corps had already lost interest in the project, terminating development in May 1947. Modified from the Boeing B-47B Stratojet, a 6-engine jet-powered strategic bomber, the Boeing XB-47D was an attempt to increase the bomber's range without the need for aerial refueling. This would be a 4-engine design, replacing the inner 2 engines from each wing with a single Wright YT-49W1 turboprop. The YT-49 itself was a license-built Armstrong Siddeley Sapphire turbojet and modified as a turboprop. Unfortunately, yet unsurprisingly, this modified engine was the cause of numerous delays and problems, and it failed to pass its 50-hour qualification run. This prevented the aircraft from taking its maiden flight until August 1955. During testing, the XB-47D achieved a maximum top speed of 518 knots, making it one of the fastest mixed-powered aircraft ever built, excluding those with rocket hybrid systems. To achieve such speed, all engines were set to maximum power output, resulting in excessive fuel consumption, contradicting the entire purpose of the project. Optimal cruise speed was 402 knots, significantly slower when compared to the 484 knots of the B-47E. A combination of project delays, insufficient performance, and the introduction of the Boeing B-52 Stratofortress meant the XB-47D was doomed from the start. Ultimately, the project would be canceled, and both prototypes were lost to time, and presumably scrapped. As the mixed propulsion series started with the Ryan Fireball, it's only fitting to end it on the successor, the XF-2R Dark Shark. Unlike the Fireball, which used a piston engine, the Dark Shark instead used a General Electric T-31 turboprop mated to a large four-bladed Hamilton standard propeller. It maintained the same General Electric J-31 turbojet inherited from the Fireball. To further improve performance, Ryan proposed a design replacing the J-31 with a Westinghouse J-34. This proposal, however, never made it off the drawing board. The large turboprop greatly improved the performance of the aircraft, now giving it a top speed of 497 miles per hour. Inheriting the stability and favorable flight characteristics from its predecessor, the Dark Shark proved to be a capable aircraft. However, it too was terminated as the Navy lost interest in the mixed propulsion concept. Before we conclude this episode, let's go over some honorary mentions. This will briefly cover aircraft that saw limited modification with mixed propulsion, modifications that never flew, and designs that used rocket propulsion. The Douglas XB-42 Mixmaster was a promising piston-driven bomber design that could have been a game-changer in a piston-driven world. However, it found itself becoming obsolete during the testing phase as jet technology leapt forward. In an attempt to stay relevant, it was modified with two Westinghouse 19XB turbojets. The design would later be refined into a purely jet-powered version, designated XB-43 Jetmaster, which also failed to earn a production contract. This Grumman OV-1A Mohawk was modified by the Pittsburgh Institute of Aeronautics to fit two Westinghouse J-34 engines under the wings. It never flew in this configuration, but was instead used as a ground-based platform for engine runs. From what little information there is on this subject, it seems that the Institute was denied permission to build a proper static test cell for engine runs. However, no rules existed denying the engine runs on an actual aircraft, resulting in this modification to act as a loophole. This modified Gulfstream II, operated by NASA, retained the original two Rolls-Royce turbofan engines, but the left wing was modified with an Allison Model 570 turboprop engine mated to a prop fan-type propeller. It was used to research the prop fan concept and gather data on noise levels. The Boeing KC-97L was just a standard KC-97G aerial refueling and cargo transport, modified with two General Electric J-47 engines in underwing pylons. Much like the KC-97L, the Boeing KB-50J was modified to house the same J-47 engines. However, the J designation was universally applied to all 112 B-50s, modified for mixed propulsion. These were modified from D, E, F, and G models. The Republic XF-91 Thunderceptor is a highly unique aircraft that may get a video of its own at some point. However, all that is relevant today is the afterburning General Electric J-47 conventionally mounted in the tail and the experimental liquid-fueled rocket motor. With both engines running, the XF-91 could reach a speed of Mach 1.49, making it the fastest variant of the F-84. Used by NASA to train astronauts for the X-15 program, the NF-104A was your normal starfighter modified with a reaction control system, or RCS, and a Rocketdyne liquid-fueled rocket motor. A typical flight profile in this aircraft would launch the aircraft above 100,000 feet, with the highest achieved altitude just shy of 121,000 feet. Multiple aircraft throughout history have been used as testbeds to research the new technology. This Boeing B-17, nicknamed Liberty Bell, was used to test the Pratt & Whitney T-34 turboprop. Here is another one, designated JB-17G, modified to test the Allison T-56. A few North American P-51s would also be used to research captured pulse jets. NACA would use a Northrop P-61 to research early ramjets. In conclusion, there was no shortage of enthusiasm towards mixed propulsion designs. In theory, it would provide the best of both worlds. However, in practice, such designs were often too complex to be practical. The concept was most successfully used when augmenting pre-existing piston designs to act as a stopgap solution, bridging the gap between the piston and jet eras. While many designs showed promise, they could never truly outcompete the quickly advancing jet designs.